Welcome back to A320 Knowledge, your trusted source for Airbus expertise. Today, we're diving into Airbus's guidance on engine failures above the thrust reduction altitude. Now, for those unfamiliar, thrust reduction altitude is a defined altitude above ground level where engine power is reduced to climb thrust after takeoff. This can be for both noise abatement reasons and for longer-term engine health. While engine failure at V1 is a well-rehearsed scenario in simulators, a failure at thrust reduction altitude remains a less familiar concept for many pilots. Airbus has specific guidance for this situation, so let's dive right in and take a closer look at it.
During this presentation, I would like to talk to you about engine failure above the thrust reduction altitude. So engine failure at takeoff, but after the flight crew moved the thrust lever position to climb. But before we talk about engine failure, let's talk about fuel savings. Nowadays, fuel is really expensive. We can all agree fuel is an important subject in today's airline industry. This is a non-exhaustive list of operational fuel efficiency initiatives some airlines have implemented. For example, single-engine taxi enables to save fuel, especially at congested airports. The use of idle reverse at landing also enables to save fuel. Each of these initiatives enable to save a small quantity of fuel per flight. But multiplied by the number of initiatives in place and the number of flights, this can really make a difference. Decrease the thrust reduction and acceleration altitude is one fuel efficiency initiative as well. Decreasing the acceleration altitude reduces the drag and is therefore good for fuel. Thrust reduction, on the other hand, has low impact on fuel, but we usually decrease thrust reduction as well so that the thrust reduction altitude is equal to the acceleration altitude. So in the end, we reduce both the thrust reduction and the acceleration altitudes. But have you thought about the impact on performance? This presentation aims at discussing the impact of an engine failure above the thrust reduction altitude on obstacle clearance. We will first look at how the engine out acceleration altitude, thrust reduction and acceleration altitudes are defined. Then we will look at the performance impact to finally work out a solution together. This presentation is really about making airlines aware of the performance impact of reducing the thrust reduction and acceleration altitudes and highlighting the existing solutions. Let's start with the definition of engine out acceleration altitude, thrust reduction and acceleration altitudes. During cockpit preparation, pilots enter in the FMS both engine out acceleration altitude, all engine thrust reduction altitude and all engine acceleration altitudes. Let's have a look to the constraints that impact the selection of those altitudes. The engine out acceleration altitude is determined by regulatory constraints, certification and operational regulation. It assumes a takeoff flight path with engine failure 1 second before V1. The minimum engine out acceleration altitude is limited by the regulatory value 400 feet, obstacles or airline policy. The maximum engine out acceleration altitude is limited by the 10-minute use of TOGA. The aircraft must be in clean configuration and at green dot speed within 10 minutes. The engine out acceleration altitude can be determined using a takeoff chart or a takeoff performance application. On the chart, the flight crew can find the minimum and maximum QNH altitude, taking into account the regulatory constraints. With the takeoff performance applications, the flight crew directly gets the engine out acceleration altitude, taking into account the airline policy. The thrust reduction altitude and acceleration altitude are all engines parameters. They are determined taking into account operational considerations. They are not strictly defined in the regulation. The operational considerations that are taken into account to determine the all-engine thrust reduction and acceleration altitude can be SID constraints, it can be obstacle or ATC, noise, like NADP procedures, it can also be due to fuel efficiency consideration. The constraints are totally independent. There is no link between the engine out acceleration altitude and the all-engine thrust reduction and acceleration altitudes. Today, due to fuel efficiency and noise constraints, operators tend to decrease more and more both all-engine thrust reduction altitude and acceleration altitude. But these surely have an impact on performance. Let's look at it together. Let's consider a takeoff flight path. In this example, the engine out acceleration altitude is 1,500 feet. The all-engine acceleration altitude is 800 feet, and the all-engine thrust reduction altitude is 500 feet. Here we have the thrust reduction altitude, which is below the engine out acceleration altitude. Here in red, we have the takeoff flight path considering an engine failure at V1. This flight path fulfills all regulatory constraints and particularly ensures that the net flight path clears obstacles with a 35-feet margin. In green is the flight path with all engine operative, taking into account a thrust reduction at 500 feet and an acceleration at 800 feet. Thrust reduction and acceleration altitudes have been determined in order to comply with all engine constraints. The flight path with all engine operative, of course, always remained above the flight path computed with engine failure at V1. But what happens if an engine failure occurs after the thrust reduction altitude? The flight crew is in climb. The most critical case in terms of performance is engine failure just after reduction. Is this a scenario to check? In that case, lever MCT flashes on the PFD. When the pilot sets the thrust lever to max continuous thrust, the aircraft climbs at constant speed, V2 plus 10, up to the engine out acceleration altitude, where the pilots initiate level off and accelerate to green dot speed. The flight path becomes the yellow one. With such yellow flight path, the obstacle clearance might not be ensured anymore in those two areas with max continuous thrust. Such issue only happens if the thrust reduction altitude is below the engine out acceleration altitude. Let's consider a second example, the case of an engine failure at the acceleration altitude. Again, lever MCT flashes on the PFD. When the pilot sets the thrust lever to MCT, the climb mode remains engaged. The aircraft will simultaneously climb and accelerate to green dot speed. As the aircraft tries to climb and accelerate at the same time, the resulting climb gradient is low. The aircraft climbs up to the engine out acceleration altitude, where the pilot initiates the level off and continue acceleration to green dot speed. The flight path is the yellow one. Again, with such yellow flight path, the obstacle clearance is not ensured anymore in this area with max continuous thrust. If no obstacle, this is not a problem. But what if there are obstacles? This is not a new problem, but it is true that we more and more reduce the thrust reduction and acceleration altitudes. So finally, it is more of a constraint today than it was before. What could be the solutions? Increase the thrust reduction and acceleration altitude above the engine out acceleration altitude, but it is not efficient in terms of fuel. A detailed performance study can be done to ensure that setting max continuous thrust ensures the obstacle clearance, but this requires significant workload and the result may lead to increase the thrust reduction and acceleration altitudes as well. In fact, there exists an alternative solution, to set toga thrust after the engine failure. In terms of aircraft performance, the solution is easy. Putting toga back always works, without additional detailed study. But can I put toga back? The answer to that question is yes, toga always remains available. The FCOM says, if necessary, move the thrust lever of the active engine to the toga detent. On system's point of view, it is possible to set toga back. Let's have a look to what happened on the takeoff flight path. In the case of an engine failure at the thrust reduction altitude, lever MCT flashes on the PFD, but the pilot can disregard it and set toga. In that case, the SRS takeoff mode remains engaged and the aircraft will climb at constant speed V2 plus 10. As the thrust available is higher than MCT, the climb gradient is higher. The aircraft climbs with this speed up to the engine out acceleration altitude, at which the pilot initiates the level off and start acceleration to green dot speed. This flight path with toga thrust always remains above the flight path considering an engine failure at V1. The problem of obstacle clearance is solved. Let's now come back to the case of an engine failure at the acceleration altitude. Lever MCT flashes on the PFD, but the pilot can disregard it and set TOGA. In that case, the SRS go-around mode engages and the aircraft will climb at constant speed. This speed is equal to the maximum of VAPP and current speed limited to VLS plus 15. The aircraft climbs with this speed up to the engine out acceleration altitude, at which the pilot initiates the level off and starts acceleration to grid dot speed. This flight path with TOGA thrust always remains above the flight path considering an engine failure at V1. The problem of obstacle clearance is solved in that case as well. Using TOGA, obstacle clearance is always ensured by the engine failure at V1 case. I need to highlight at this point that we have such issue with obstacle, but this question is not specific to engine out SID. Even if the procedure in case of engine failure at takeoff is to follow the SID, it can be a constraint. Remember what we said in introduction. This presentation aimed at making you aware of the performance impact of reducing the thrust reduction and acceleration altitude. Engine failure after the thrust reduction altitude is not covered by regulatory calculations. With max continuous thrust, obstacle clearance might not be ensured if the thrust reduction altitude is below the engine out acceleration altitude. But TOGA remains available. This is not a new subject, but it is true that it is becoming more of a constraint with the implementation of green operating procedure. Put TOGA back enables to take benefit of the fuel efficiency procedures without any additional study. We therefore decided to clarify the Airbus documentation in order to incorporate a clear statement to highlight that the use of TOGA thrust can be a solution in case of obstacle constraints. Thank you.
Thanks for tuning in to this tutorial on engine failures above thrust reduction altitude.